Hello, my name is Sandeep Reddiwari. I am from School of Computing, University of North Florida, USA. I am presenting my paper on the use of visual clustering to identify landmarks in code navigation. So this is my outline of the presentation. So first I'll talk about the introduction, problem statement and proposed solution, and I briefly introduce the background and related work in the code navigation area, and I'll present my research methodology, quantitative analysis and the results, and finally I'll present my conclusion and the future work of this paper. Coming to the city navigation, we know people always get lost while navigating a city. So if you see the picture on the right side, so the picture shows an aerial view of New York City. So moving in a city without navigation is almost impossible without assistance such as any GPS devices. So navigation in city requires high level of attention and persistence. So people always use GPS devices to navigate a city, and also some people, they always use landmarks such as any prominent features in a city, or maybe street names, or any points of interest, or maybe intersections, so that they can easily navigate in a city. Software navigation is also similar to city navigation in many ways. For example, in city navigation, people always go from one point to another point, whereas in software navigation, so people always go from one code file to another code file in order to solve a particular maintenance task. So software space can also be depicted as a real world city. So the right side picture shows that software as depicted as a city, so where you can see the blue vertical bars. So each vertical bar indicates a software package or a module. So the navigation through software space requires similar attention to details as we have seen in case of city navigation. But unfortunately, so there are no maps or directions are available in software space to assist programmers. The limited assistance through tools are complicated and also time consuming. These days most people are using intelligent IDEs such as Eclipse, NetBeans, Visual Studio in order to develop their projects. So according to source code navigation literature, so code navigation is considered to be the most time consuming and tedious process in the software engineering life cycle. According to research, code navigation is defined as the process of direct or indirect searching of information in software space, and code navigation is also concerned with the strategies developers use to find relevant areas of concern in source code. So, and also research says that substantial amount of time is spent on navigating through the source code. So as shown in the below figure, a particular developer starts at a certain point in the code, navigates through the entire code base to perform enhancement or software maintenance activity. So sometimes developers keep revisiting already visited locations or explore locations. Code navigation is a crucial activity in software maintenance. So, and also this is central to program comprehension and instrumental to software maintenance tasks. So despite the support offered in contemporary software development environments, code navigation remains a time-consuming and difficult task. For example, when using Eclipse to perform software maintenance activities, 35% of developer time was spent in navigating through the code, and 76% of all navigations referred back to the locations that had already been visited. A major challenge is to understand the fundamental mechanisms underlying developers' code navigation behaviors and further develop tool support to augment their information seeking skills in software maintenance. So in the paper we argued that identifying landmarks is particularly relevant to reverse engineering because by recovering the essential legibility features, not only can programs be understood at a level of reduced complexity, but software evolution can also be tackled in a well-organized manner. This is our proposed solution to the problem that we stated. So our proposed solution is threefold. So first, we identify static dependencies among various Java files and software modules. In the second step, we apply visual clustering techniques to depict, explore, and analyze the visual software clusters. So to that end, we developed an automated software tool called as SDVisu, which is static dependency based visualization. So this tool, SDVisu, depicts all the dependencies and clusters and helps developers to navigate from one cluster to another cluster, from one module to another module, or from one package to another package. In the third step, we identify landmarks using the tool SDVisu in the source code so that developers can easily navigate through the source code. Okay, so I briefly present the background and related work of software clustering and visual clustering. So software clustering techniques are employed commonly to aid the reverse engineering process. So these techniques attempt to automatically discover natural groupings of large number of software entities, such as the set of all files comprising a software system. So the goal of these techniques is to decompose the problem of understanding a large piece of software into smaller and easier to manage subproblems by reducing the effort involved in recovering the overall system structure. And also there are many other benefits of source code clustering. Just to name a few, source code clustering facilitates program comprehension and software maintenance. A diverse range of software clustering approaches has been presented in the literature. So these approaches differ in the underlying mechanisms. For example, deducing clusters from file and procedure names, computing a measure of structural similarity between software entities, minimizing the information loss during the group of entities, or treating clustering as an optimization problem. So we reviewed all these software clustering approaches, and we classified these techniques into three main categories. So one is pattern-based clustering, evolutionary clustering, and collaborative clustering. So pattern-based clustering forms clusters based on the familiar subsystem structures that frequently appear in manual decompositions of large-scale software systems. So evolutionary clustering mines the co-change relationships from the software revision repositories. And coming to the collaborative clustering, so basically this clustering exploits projects, teammates' navigation history to group and recommend software entity. In most software clustering approaches, the results are presented using flat lists or hierarchical dendrograms where the clusterings are depicted. The visualizations are rather illustrative than schematically rigorous. So, but again, coming to visual clustering, it advances the literature by attempting to ensure the drawn layout fulfills the desired clustering properties. In particular, the software entities to be clustered are represented as nodes of a dependency graph. So a visual clustering algorithm then maps each node to a position in the two-dimensional space. So the layout can be computed by force-directed graph drawing, which we explained in our paper, and also we used Lindlog energy model, which is proposed by Novak, which is also explained in the paper. So we have adopted Lindlog energy model to efficiently depict the software cluster. Coming to the software exploration and software legibility, so we were motivated and inspired by Lynch's seminal work on wayfinding. So he studied people's organization of the spatial information about an urban environment. So as part of his findings, so he identified 5 legibility features which are generic to people when describing the model of a city. For example, landmarks, which are prominent features, paths, nodes, districts, and Lynch in his seminal work defined landmarks as prominent features in a city, such as monuments and shop fronts, and paths as streets or footpaths that allow the observer to travel through a city, and nodes means important points of interest along paths, for example, street intersections, bridges, or town squares. So districts means basically areas. Edges means boundaries to areas that form basically a physical barrier to travelers. So studies show that the more legible an environment is, the easier it is for people to navigate around, recognize a location, and determine a route. So the same thing applies to source code navigation. So improving legibility features such as landmarks are crucial for generating stronger models, which makes it easier to comprehend and maintain software systems. So landmarks in software space are defined as, so landmark is a dominator node which has paths to all subsystems and connected to large systems or modules. So Lawrence et al. Recognized the signposts in source code model queues for debugging process. So here in this work, we are concentrated towards automated ways to identify landmarks in software space and relate them to programmers' actual code navigation. This is our research methodology. So coming to the research objective. So the objective of our work is to explore to what extent can the legibility features identified by visual clustering support developers' code navigation. So to answer the research question, so first we define the navigational landmarks, and then we describe the research instrumentation by presenting our visual clustering implementation for recognizing the static dependency based landmarks in software space. So we define landmarks as programming elements referenced frequently by developers for program comprehension or software maintenance activities. So a landmark may reflect programmers' current task, a particular browsing pattern, or any idiosyncrasies within the source code. So in order to assist programmers, we leveraged visual clustering to generate holistic view of landmarks considering the entire software space. In order to visually explore the software clusters, we developed a visual clustering tool by concentrating on static dependencies in the code base, and then we call this tool extension as SDVisu, also known as a static dependency based visual clustering. So the output of visual clustering is a holistic picture that can effectively convey the landscape of the software system. So two attributes of the visual clustering result are worth mentioning. One is layout and distance. So in the paper we provided all the details about our underlying clustering algorithm and also underlying energy model. So this is the screenshot of our SDVisu tool where you can see 4 different areas. So A indicates this area, indicates the number of clusters and the overall software space, and B, which is the basic control panel, and then C, which is the advanced control panel where you see advanced options, and then D, it's basically the zoom in view functionality of our SDVisu tool. Now I'm going to demonstrate our SDVisu tool. Okay, so this is our project, SDVisu. Let's run the project. Okay, so this is the tool. Okay, so this is the basic control panel, and if you click advanced, you will see the advanced control panel, and then there is an option called load, and then you can select a particular file. For example, I have selected mylin.rsf. So RSF stands for relational standard format. Let's open the file where you can see this beautiful clustering layout. So the design intent of SDVisu is to support developers in exploring the static dependencies in the source code via quantitative visualizations. So the input of SDVisu is the dependency graph, whose nodes are source code files and edges are static dependencies between the files. For example, the input that we gave to the tool is mylin.rsf file. So Mylin is basically an open source Java project under Apache license. So we extracted all the static dependencies from the Mylin, and then the tool takes the input dependency graph as the input. Okay, so these are, and as you can see, different incoming edges, incoming and outgoing, and you can see the log data, file analyzer feature, cluster analyzer. So let's go to file analyzer. Okay, so here the default number of iterations is 100, so I can change the iterations, and then you can run the layouter. Okay, so this is the cluster layout, and then there is an option called show dependencies. If you click that option, so you will see the dependencies among the code base. So there is another functionality. It's called zoom in functionality, where you can zoom in and then see the dependencies in a file. So there is label options. If you select show, it's going to show all the labels. For example, if I click this node, so then it's going to show you the label of that particular file. So let's hide the labels, and then if you click that node, it's going to show the name of that particular Java file. And then we implemented cluster analyzer features. Okay, all right. So here each green node indicates one Java file. Okay, so an edge indicates the static dependency between those Java files. So each visual cluster groups the source code files into a coherent area. So SDVSU employs force-directed drawing layout, which balances the forces of all the nodes in a cluster. So the size of the node here is proportional to its edge degree, which means the larger the node, the higher